We've already learned how to differentiate and integrate exponential functions, but today we're looking at specific examples of exponential growth and decay questions. Now, there's a certain type of question that we need to be able to work through because we get these nearly every year in the HSC. Now, I've put a typical exponential growth or decay equation up here. I've got P being a population, but it could be Q for quantity or V for volume or anything you like. In this case, P0 is the population at the beginning when time is 0, T is time, and K is just a constant. Now, for an equation that sits in this form, there's certain things that always happen. If we differentiate it, then we know that the constant, this P0, stays there. And we also know that we have to differentiate what's up here in the index, and that has to come down the front. Now, we're differentiating here with respect to the time. That means we're seeing how many T's we've got up there, and of course we have K of those. So when we differentiate this, we get the K coming down the front, and then we have to rewrite the constant that comes along, and then we have to rewrite the exponential expression. So we know that we can get that. Now, it turns out that all of this part has just been rewritten, hasn't it? And this happens every time. So in effect, what we've got here is we could sub this in and say, well, we've got an expression for all of that, it's just P. So what we've got here is actually just K, P. Now, what does this mean? Well, it means that the rate of change of the quantity, in other words, the change in the quantity or the population with respect to the time, is actually proportional to the size of the quantity at that time. How do we know? Well, the change in this population over time is just a constant multiplied by whatever the population is. So we've considered this before, but we haven't actually worked through questions, and we always get questions in the HSC that say, show that dp dt, say, is equal to kp. They'll say, show that this. And you'll have to then basically go through these 3 steps to show this. Now, why do we get this situation in nature where the rate of change is proportional to the quantity? Well, it makes complete sense. If we've got a population that's growing, let's just say it's rabbits multiplying, the more rabbits there are to reproduce and have children. And so the number of rabbits at any one time is definitely related to their ability to reproduce. Similarly, if you're looking at decay, something like perhaps the half-life of a radioactive substance, the more substance there is, the more there is to halve, or the less there is to halve, whichever way you think of it. So the amount that's there is definitely related to the amount that it drops each time. So we call this situation exponential growth and decay, and it's the exponential growth because it's using E, not just 2 raised to some power or 3 raised to some power, but E. And this is the type that we see in nature all the time. Now we call K the constant of proportionality because that's the special number that for that situation will be the number that you multiply by the population at any one time to work out what the rate of change actually is. Now if K is negative, then we've got exponential decay, and we've already seen that you can write it with K being a positive number and just putting a negative out the front, or you can write it without a negative out the front and know that K is a negative number. Now, a couple of tips. When you've got an equation in this sort of form, and it might be P or it might be Q for quantity, V for volume, something like this, notice that when time equals 0, we get e to the power of K times 0, and that gives us e to the power of 0, which is just 1. So this whole section becomes 1 when time equals 0, and that means that P just equals P0. Now, how does that help us? Well, this is actually a little proof that that constant that's sitting in front of the index expression is always the quantity at time equals 0 for equations that are written in this form. So there's 2 ways you can get these questions asked. It might be a worded question where they just say, initially there were 20 rabbits or something like that. So you know, right, when t equals 0, the quantity was 20. Or they might give you the equation and say rabbits are reproducing such that the quantity of rabbits is, say, 20 e to the kt. Now, by giving you the equation, they have literally given you now the starting condition, which is that at the start, when t equals 0, there must have been 20 rabbits. Now this only works if it's in this form. If it's got something added onto the end, of course it wouldn't work. But that's a good tip, knowing to look out for that number there as being the initial condition. All right, there's also three unknowns in this section of the equation. There's the constant out the front, and there's k, and there's t. So if you want to find one of those unknowns, you need to know the other two. So questions will often give you the initial condition, as we've discussed. They might give it to you as an equation, which has got it in there, or they might say at the start there were, say, 20 rabbits. But they'll need to give you some other clue. For example, they might say, after a year there were 100 rabbits. So that you'd say, okay, so when t equals 1, the quantity was 100. You need that clue so that you can find the value of that constant k. Now, many of these questions actually do start this way, so it's useful to think this through. When you find k, it's nearly always going to be a complicated little log expression. And when you use it in later parts of the question, you don't want to waste time putting it into your calculator each time. So once you've found k, store it in your calculator for later use. And you do that by pressing the Shift button and then the little yellow store, which is, you do Shift and then the store, which is on the RCL button. And then choose one of these red letters. Normally I just choose A. And then when you want to use that value, which is now A in your calculator, and you can hit the all clear and do a heap of other things with the calculator, but when you want A, hit alpha, because that brings up the red functions, and then hit A again, and you can use it just like a number. So you can do A squared, A times 20. You can use it in your calculation. Super handy and a big time saver.